So, hi everyone, and thanks for being here. I'm giving my research seminar for the opening at the University of Florida, and I'm going to be talking mostly about charge transfer and chemical reactivity. I'm actually now at York University, like postdoc at York, but we are actually doing this recording at McMaster University. I'm here, and thanks to all the guys from the Institute for being present today. So, my research up to today, since like 2006 when I started working on quantum chemistry, has been mostly devoted to the study of electronic structure. And we have two main groups of research that we can do in this topic. On one side, we have developing new accurate methods to study electronic structure, and I'm going to be talking about this on my proposal seminar next week on Wednesday. And now I'm going to be talking mostly about how to gain actual chemical insight from these more accurate calculations. I have done some work on this using different methodologies, like for example density matrices and molecular comparisons and some sort of like structure relationship activities. But now I'm going to be talking mostly about my work on conceptual density functional theory, which was the main topic of my PhD. And that research has been like carrying on until today mainly. I'm going to be introducing the framework. I'm going to be talking about the problem of how the energy is changing with the number of particles and how this is so relevant for conceptual DFT. I'm going to be talking also about the environment perturbations and how we take into account how different molecules interact in this framework, and then discussing some simple yet like pretty like nice applications of the work that we have been developing so far. So first of all, conceptual density functional theory. In a moment, we are going to be seeing why we should call this why we should be calling this framework actually conceptual density functional theory. But also by the end, we will be like seeing why actually we should not be calling this conceptual density functional theory. So far, let's just present the basic idea behind conceptual DFT, and it's actually a surprisingly simple idea. So we know that if we have the wave function of a system, we can actually know all the properties of the system. And we know that in principle, we can get the wave function by solving Schrödinger's equation. And this is extremely complicated, but in principle, all we need to know to solve Schrödinger's equation is just the Hamiltonian of the system. And to build the Hamiltonian of the system, all we need to know are just the number of electrons of your molecule or your atom and the standard potential, meaning basically the geometry of the nuclei that you will have in your system. This means that we can actually describe any process by just analyzing how the number of electrons and the standard potential will change along a reaction, for example. If we have two molecules that are interacting with each other, we just need to describe how electrons and standard potential will change. In a more mathematical sense, this means that we can expand the energy for what matters, any other state function, using just a Taylor expansion on the number of particles and the standard potential. This is the basic idea of conceptual DFT, and the thing is that we are actually not using this Taylor expansion to calculate energy differences. The main importance of this framework, of this idea, is that the coefficients of this expansion can actually be used to provide definitions for multiple chemical concepts. For example, the first derivative of the energy with respect to a number of particles, we can actually identify that as the chemical potential of the system, which actually in turn provides a definition for the electronegativity. And this is actually quite simple to grasp. Let's say we have two fragments or two molecules competing for some electrons. Obviously, the fragment that will gain the electrons is going to be the fragment that will like gain more stability by gaining these electrons. This means that the fragment that will be gaining the electrons is actually the fragment for which minus delta E over delta N is going to be bigger, meaning that we can actually take this magnitude as a measure of electronegativity. In the same way, the second derivative of the energy with respect to a number of particles, of number of electrons, can be identified as the chemical hardness that Pearson proposed like close to 50 years ago. And we can actually show that increasing this parameter, this descriptor, actually follows all the like typical trends that we are expecting from Pearson's hardness. For example, increase charge, decrease size, or decrease in polarizability. Also, we can define many other descriptors that we can actually use to study, for example, radio selectivity, stereo selectivity, and so on and so on, from the electron density as it is, or the Fourier function, dual descriptor, or even the linear response. Moreover, we can not just define descriptors in this framework, we can also prove different chemical principles starting from actual like first principles, from, for example, the variational principle, which is actually why people started calling this, like Parr and his students, this framework conceptual DFT, because starting from the variational principle written for DFT, we can actually prove Sanderson's electronegativity equalization principle, because the chemical potential actually appears as a key factor of this variational principle as a magnitude that doesn't depend on the position on the molecule, meaning that the electronegativity will be the same regardless of the position within a molecule or an atom. In the same way, or in a similar way, we can show that using a very much simplified Taylor expansion of the energy, taking into account just the change in the number of electrons up to second order, we can actually prove Pearson's Hartsoff acid-base principle. Moreover, we can even discover new reactivity rules. For example, we can prove the maximum hardness and a minimum electrophilicity principle, meaning that the stability of a molecule will be related, for example, to an increase in the hardness or a decrease in the electronegativity. Going even further, we can actually show different relations between these principles. For example, we have been able to prove that actually the maximum hardness and the minimum electrophilicity principles imply Pearson's well-known rule. It is no surprise that in the early 80s, Parr and Young actually found a deep connection between conceptual DFT and frontier molecular orbital theory, because actually we are talking about two different theories to explain chemical reactivity. And for example, Parr and Young proposed this Foucault function actually as a, I would say, correct generalization of the HOMO and LUMO densities for the cases that we are, for example, working with a correlated wave function. So this provides a very strong link between conceptual DFT descriptors and frontier molecular orbital theory. Moreover, using a Maxwell relation, Parr and Young actually proved that the Foucault function is just the response of the chemical potential of the system in terms of the external potential of, let's say, for example, a reagent that is approaching our system. This means that if we could actually prove that increasing the response of the chemical potential to an external perturbation is a favored process, we can actually find a proof for frontier molecular orbital theory starting from first principles. This is what Parr and Young coined as the delta mu weak is good principle, but this remains a conjecture for over 30 years, which is actually something not so common in chemistry, that we have like a statement that we cannot prove for over a decade. So proving this statement would actually mean that we could prove frontier molecular orbital theory starting from a stronger basis, like for example, just DFT. And actually we did this last year, so we actually provided the first proof for this principle when we show that when we have, for example, a molecule reacting with any two given reagents, A would prefer to react with a reagent that would actually increase the response of the chemical potential. Also, we prove that if we have two different molecules that can interact in multiple ways, the way of approaching these two reactants will be the way that actually maximizes the response of the chemical potential. Moreover, we also show that from this simple principle, we can actually prove Pearson's Hartsoff acid-base principle, we can prove the maximum hardness, and we can prove even the minimum electrophilicity principle. So now we have actually a framework that not only explains frontier molecular orbital theory, but also we can explain most, if not all, of conceptual DFT, starting from a really simple chemical rule. So at this point, we know that we have a framework, conceptual DFT, from which we can have access to different concepts and different principles that we can use, for example, to study chemical reactivity, spin transfer, charge transfer. We can apply this to drug discovery, to materials design. We can even use conceptual DFT to design new force fields. And this is actually really, really nice that we have such a unifying framework. But we have been omitting a very important detail. And this is that if we have a Taylor expansion for the energy in terms of the number of particles, this means that we need to take the derivative of something, for example, the energy, with respect to the number of electrons, meaning that we have to consider real number of electrons, like non-negative number of electrons. And this might sound a bit weird at first, but for example, there are like multiple ways we can go around this issue. For example, Parr proposed that we forget about the non-integer number of particles, and we actually approximate these derivatives as the fraction of finite differences, so the quotient of finite differences. There are many ways to go around this, approximating these fractions, and for example, we can use first order finite differences, which essentially means that we will be taking like straight lines joining integer number of particles. So we will have, for example, a derivative when the system is losing electrons, a derivative when the system is gaining electrons. We can also use second order finite differences, meaning that we essentially fit a parabola every 3 consecutive points, and we get like a smoother behavior for all these descriptors. At this point, there is no real way to say which of these procedures is the more convenient or is the one that has the firmer theoretical grounds. Moreover, there are even people that combine first order and second order descriptors, and actually the main motivation for all this work was saying like, okay, so we want to know actually how the energy is changing with the number of electrons, and if we can actually mix match different approaches in the same expression. So starting with this problem, we actually look at a more general situation. So we look at the problem of a spin resolved conceptual DFT, meaning that we are taking into account not just the number of electrons, but we are actually separating the number of electrons in the number of alpha or beta electrons, or for example, the number of electrons and the spin number. Meaning that in principle, using this new more general framework, we can actually study radical reactions or, for example, bond breaking, like more general processes. And the key to this study was actually to find the minimum quantity in which we can change one of these variables, keeping the other constant, in a way that we always keep moving from integer number of particles every time. So let's think, for example, about this grid, and it's essentially finding the minimum step such that at every intersection we only have integer number of particles. Let's say alpha or beta electrons on number of particles and the spin number. These numbers are actually pretty easy to obtain. We have the values here, and using this key insight, we were actually able to find the expressions for the relativity descriptors for first or second order, for basically all the relevant descriptors in this framework. So this is actually the first time that we can obtain all these expressions starting from a single idea. So this is actually the first general framework to study spin reactivity. These formulas are exact as long as we are using the exact energy differences, but to compare our results with the literature, we need to do introduction approximation, which is what everyone does when working with finite differences, and that is approximating the exact energy differences using orbital energies. Like, for example, when we are getting an electron, we use the energy of the LUMO orbital, and when we are losing an electron, we actually use the energy of the home orbital. And if we introduce these approximations in our exact equations, we actually find that all the expressions that we obtain are equivalent to expressions previously proposed in the literature, with one exception, and that is the spin hardness that we find has this working expression. But the problem is that previously Vargas, Galvan, Vela, and others have been using these other expressions since like almost 20 years ago. We gave many technical reasons of why this expression is not right, but let's just mention that, for example, it is pretty easy to see that the hardness expression of Vargas et al. Will always be negative, or at least non-positive. And this cannot be true, because if this is the case, we will be actually breaking the electron convexity that we know as an experimental fact that this cannot happen. On the contrary, we can actually see that our expression for the spin hardness is always positive, meaning that it will actually preserve the energy convexity when we change the spin number. So now with this in mind, we actually analyze the work of Ola and collaborators, where they analyze a set of carbines, silylines, and germylines with different singlet and triplet ground states, and essentially they use a Taylor expansion, like a truncated Taylor expansion, to predict the single triplet gaps in these systems. They use a second order Taylor expansion, but using the first order chemical potentials and the incorrect hardness of Vargas, Galvan, and Vela. They obtain results that are not so bad, taking into account all the approximations, but the problem is that we know they are using an incorrect form for the hardness. So what happens actually when we use what we say the approach of mixing different descriptors with the correct expression for the hardness, then we see that the errors escalate more than 10 times, meaning that actually what they were obtaining is just a cancellation of errors, because in this, like in a wrong way, this hardness is negative, they were actually cancelling the effect of actually adding the chemical potential using a first order descriptor, meaning that we could prove that actually we should not use different E versus M models at the same time. So we cannot use a first order descriptor in a second order expression for the energy. That makes like no sense whatsoever. But proving this actually is not showing us what model, what E versus M model we should use. And to do that, we actually need to consider fractional N. So the idea of fractional number of electrons at first might seem a little shocking, but actually it's pretty natural if we recognize that fractional electron number may arise as a time average on an open system, meaning that the number of electrons is actually variable on the system, meaning we have an open system. On average, we can have, for example, 4.5 pi electrons, E electrons, or any non-negative number. This actually has a pretty deep implication, and that is that we cannot describe the systems using a wave function, because wave functions are just for closed quantum systems, that we need to actually use a more general description of a quantum state, meaning that we have to use a grand canonical density matrix. And these have this structure right here, that actually we are just using an incoherent superposition of pure states, where these omegas are just giving the probability of finding your state in any of these pure states. And since these omegas are just probabilities, we know they must be non-negative and they must be normalized, meaning that you will always add to 1. So the simplest family of models that use this inside of fractional N are what we call interpolation models, and they are just what the name suggests. We just take the points with entire number of particles, and we essentially fit a polynomial, a parabola, a linear functions, exponentials, or essentially whatever function you want, just making sure that you will be touching every entire point. And the key of this kind of models, like the defining feature of these models, is that whenever we have an entire number of particles, the state of the system will be only given by the wave function of that entire number of particles. So we collapse the whole density matrix to one wave function. In a more mathematical way, this means that of all the omegas describing the probability of these density matrices, we know one of these omegas is going to be actually equal to 1, and all the others are going to be identically 0. However, this has a really a strong implication, meaning if we could actually differentiate these omegas, and we need to differentiate the omegas to get the chemical descriptors, since 1 is the maximum value and 0 is the minimum value, we know for sure that these derivatives are actually going to be equal to 0, meaning that the chemical potential for any system at any number of particles, given that the number of particles is an integer, is actually going to be just 0. And this has a really a strong chemical implication, meaning that, for example, the electronegativity of fluorine is going to be actually equal to electronegativity of fluorine 7 plus, and that's actually going to be equal to 0. So this implies that fluorine is actually going to be a perfect electron donor, which we know for sure is not the case. In other words, we cannot have at the same time a grand canonical description, we cannot have differentiability, and we cannot have interpolation. And since we know we cannot give up a grand canonical description, this means we need to abandon differentiability or abandon interpolation. So we cannot live with all these three at the same time. To actually see what we need to throw away out of the window to keep going with conceptual DFT, we actually need to go like the full grand canonical description. And to do this, we first start with isolated systems at absolute zero. And in this case, we are actually just taking into account, so the main problem that we want to solve is finding the ground states of the system. To do this, we solve using the variational principle for the energy, just minimizing with respect to the density matrix, and this actually has a really simple solution. And that's just a combination of two states between the number of particles that actually the system will have. And this is a really clean and a really simple solution, but this solution has two main problems when studying chemical reactivity. For one, the descriptors are not well behaved. So for example, you can either define hardness as 0 or infinity, meaning like really there is, or anything in between. So there is really no hardness at all, or you cannot define the hardness. And more importantly, under these conditions, charge transfer is forbidden. And this makes a lot of sense because we are actually talking about isolated system. The system has nothing or no one to exchange electrons with, and at absolute zero, actually this integral number of particles states are the most stable. So we need to go a bit more general and actually talk about isolated systems at finite temperature. And now the problem changes. Now we don't want to calculate or actually ground states. What we want to calculate are equilibrium states. And now the very important distinction is that we are not minimizing the energy. We are actually minimizing Helmholtz free energy, or in other words, like from standard thermodynamics, we are maximizing the entropy subject to the typical grand canonical constraints like number of energy and number of particle constraints. And this also has a really simple solution, and is this density matrix that is non-linear, actually has an exponential, and we know that exponential functions we can differentiate forever, meaning that actually at finite temperature all the descriptors are well defined. So we have chemical potential, we have chemical hardness, and you can keep derivating the energy or the electron density or whatever up to infinite order, and that will always be well defined. So finite temperature is the way to go. But we have a problem, and the problem is, okay, so now how do we define the descriptors? And there are two main, I would say, schools in how to do this. First, we have actually the Mexican school. Guys here know Marco Franco, Luis Gasquez, Jose Luis Gasquez, and Alberto Vela, and their proposal to define these descriptors is just use the same expressions that we were using at zero temperature. So the chemical potential will still be the derivative of the energy with respect to the number of particles. And this is really simple, this is really appealing, but it has a big problem in my point of view, and that is that you are actually losing the connection between the chemical potential and the electronegativity. So in this picture, no longer the electronegativity is minus the chemical potential. So the other way of defining these descriptors, and this is actually the way I propose of defining these descriptors, is to preserve the physical meaning instead of preserving the mathematical form. So the chemical potential won't be just taking the derivative of the energy. The chemical potential will be taking the derivative of the state function that is giving the spontaneity under the given conditions. And at finite temperature, that state function is the Helmholtz free energy. So now we define everything in terms of the Helmholtz free energy, and now we can recover the relation between the chemical potential and the electronegativity. Meaning that at finite temperature, also electronegativity is the one that will be governing the charge transfer between two fragments or between two molecules. Even more, using this way of defining the descriptors, one can actually find a new, actually exact way of calculating the electrophilicity of a system. And this is really something that was like shocking the first time we stumbled with this discovery, because actually we could find a definition, even more a working expression for the electrophilicity that is, first, is exact in principle, and second, is free of all the inconsistencies of the ways of calculating the electrophilicity using previous methods. Even more important, using this definition for the descriptors, we were able to prove all the reactivity principles, extending the definition, extending the previous proof from zero temperature to actually final temperature for Pearson's-Hartsoff acid-base principle, maximum hardness, and minimum electrophilicity. This looks really promising, and I mean, this is the way I'm like keeping forward, going forward with this way of working with conceptual DFT. I find a temperature, but both of these ways of working still have one huge problem, and that's that the chemical response of a system won't depend on the environment. So people usually, up to this point, I would say up to 2006, people were still thinking about conceptual DFT descriptors as something that is independent of the environment. People, for example, in chemistry, we know that it's not the same to talk about an electrophilic or nucleophilic attack. So a molecule will just respond and will react in different ways if we are just against an electrophilic reagent or acting against a nucleophilic reagent. People usually went around this problem combining first order descriptors with second order descriptors. But now we prove that we cannot do this. So this is inconsistent. So how do we actually take into account the information of the environment on the descriptors? And the way to go is actually to take into account explicitly the perturbation of the environment on the descriptors. And we can differentiate two different cases. First case is weakly interacting systems, meaning separated reagents, but they're just like approaching. I would say far away from the transition state at the very early stages of the reaction. And the best way to picture this can be, for example, from a mathematical point of view, we just add a perturbation to the Hamiltonian of every reagent. But in an even more pictorial way, we can approach this problem using essentially frontier molecular orbital theory that now we know we can actually derive using conceptual DFT. And the main idea is that when two orbitals are interacting, the orbital with higher energy will increase its energy by the same amount that the orbital with lower energy will decrease its energy. And we can actually translate this very simple picture, this very simple insight, into perturbations for the ionization energy and the electron affinity of both reagents. And with this in mind, we can actually find the expressions, for example, for the chemical potentials and for the chemical hardness of two weakly interacting reagents. And these are the first expressions ever obtained for the influence of the molecular environment on one of these descriptors. So we have these gamma parameters, for example, in the case of the chemical potential, we can actually show that they are related in this inverse relationship. So for example, now we know that when two molecules are interacting, the electronegativity of one of them is going to increase and the electronegativity of the other is going to decrease. In a different way, when two molecules are interacting, the hardnesses of both molecules will both go up or then they will go down at the same time. So this is essentially just for the case of weakly interacting reagents, and we also analyze the more difficult problem of strongly interacting systems. And this is really close, for example, to a transition state. And now we have a different problem, a totally different problem, because now we just not have to approximate, for example, the influence of one reagent over the other. We actually need to take into account the problem of defining one reagent inside this supramolecular aggregate. And this is essentially a problem of how do you define an atom inside a molecule. Since there is no unique way of defining an atom inside a molecule, we actually need to give the formalism, the freedom of working with different definitions of atoms inside a molecule. And the way to go is actually using another operators that will modify the Hamiltonian and the particle number operators that will serve as actually that will play the role of defining the fragment inside this supramolecular aggregate. And in a more, I would say, mathematical way, these actual operators, we can think of them as projection operators in the orbital space of each fragment, or actually partitioning the three-dimensional space of every reagent. And the other key insight in this approach is that if we assume that still using this fragment in a supermolecule approach, we can still measure the energy and the number of particles at the same time, meaning these operators will commute. We can still solve the grand canonical problem and obtain the exact solution for the problem of two strongly interacting reagents. And this looks exactly the same, like very similar to the problem of isolated reagents, with one key difference. Now we can have a different, in principle, a different temperature for different number of electrons. And this is a model that was proposed by Paul Ayers, like more than 10 years ago. But when Paul proposed this model, he gave no explanation whatsoever. So he just thought this was a really cool generalization, but with no justification. And now we can actually find a first principle justification for this model. Even more, and perhaps a bit surprising, we can actually solve for the chemical potential of two strongly interacting reagents. And we obtain the same expression, the same general expression as for two weakly interacting systems. Meaning that so now we are not actually proposing a new electronegativity scale. This is actually something more general. We are actually showing how the electronegativity of one system will change when these systems will encounter, let's say, a solvent or another reagent, meaning that we will have a more complete description of the charge transfer. This is also reminiscent of a form proposed by Gasquet, Cedillo, and Vela, also without any theoretical support, where they just propose using substituting 3 instead of gamma in this expression. And now we're actually showing that this form is actually way more general than what they were expecting. And this actually covers weakly and strongly interacting cases. Even more, the limiting cases of this expression will recover the first order descriptors, meaning that we can go from a fully non-interacting case to a strongly interacting case, all within the same framework. So we actually found the way to describe the electronegativity regardless of the strength of the interaction of the two reagents. So this is actually the first time that we know how electronegativity will behave under all these, I would say, spectra of conditions. So up to this point, one might say that, okay, yeah, it's cool that we have a common framework to do all this, but it would be nice if we can actually have some real applications of all this framework. And I'm going to present actually just 2 of the potential applications that we did in the past. And the first one is the analysis of dipolar cycloadditions. And these are reactions where we know that the radioselectivity is given by the charge transfer direction. So we know that given a dipole and a dipolarophile, if we know which one is giving the electrons to the other, we can actually predict the main product in these reactions. And we have 2 different cases, actually what we call LUMO control, and that's the dipole accepting the electrons. And we know the other case, obviously, is the opposite, HOMO control, when the dipole is the one giving the electrons. And we can analyze these reactions using, for example, Mulligan's electronegativity, which has no information whatsoever on the interaction on the 2 reagents. Or we can actually use our model for the electronegativity, where this alpha parameter actually is encapsulating the interaction between dipole and between both reagents. It is easy to see that if alpha is equal to this fraction, there won't be any charge transfer, meaning that, for example, since we know that Mulligan corresponds to alpha equals 1, if alpha 0 is less than 1, then Mulligan electronegativity will be able to explain the LUMO control reactions, and if alpha 0 is greater than 1, then Mulligan's electronegativity will we actually be able to predict, correctly predict, the HOMO control reactions. We study a set of dipoles, 9 dipoles and 8 dipolarophiles with using like different chemical groups, like a pretty decent variety of chemical functionality. And besides doing all the standard geometry optimization and calculating, doing the frequency calculations to make sure that we are in the actual minima of the potential energy surface, we calculate, more importantly, the ionization energies and the electron affinities using 5 different ways, meaning that we want to actually prove that the results that we are obtaining are consistent with the different ways of obtaining the ionization energies and the electron affinities. So, for the first cases, meaning for the HOMO control reactions, alpha 0 was always greater than 1, meaning Mulligan electronegativity does a good job actually identifying which is going to be the molecule giving the electrons. So who is going to be electron donor, who is going to be electron acceptor. However, in the other case, for LUMO control reactions, alpha sub 0 is also greater than 1 except for just 2 reactions, meaning that Mulligan electronegativity will most certainly give an incorrect prediction of the radioselectivity of these reactions, and that we actually need to use our framework to predict the correct direction of charge transfer, proving that actually to have like a coherent description of the chemistry of the polar cycle additions, we need to take into account the interaction between both reagents. So this is a pretty qualitative example then to go a step further and actually show a quantitative use of our new model. We are going to study redox reactions. And redox reactions are a tricky example because despite all the success of conceptual DFT studying charge transfer, up to this point, conceptual DFT had horribly failed at the time of actually explaining redox reactions. So it's no coincidence that there are almost no papers published whatsoever applying conceptual DFT to actually this prototypical kind of charge transfer reactions. So, given the scarcity of resources to study these reactions using conceptual DFT, we began doing a really simple qualitative analysis. So let's say we have a molecule that can go oxidation on 2 different ways. If we consider that the maximum hardness principle is actually valid, that it holds, we know that the main product, let's say O1 for example, will be the one with the hardest product. If we assume a smaller organization energy going from the reduced to the oxidized species, meaning that by losing an electron, the geometry of the system is not changing very much, we can actually link the hardness to the electronegativity of the different products and show that the main product will be the one with more electronegativity. So the more electronegative oxidized species is going to be the one prevailing in the end. We can actually do this same, repeating this kind of reasoning for the inverse process and actually show that the oxidation potential is an increasing function of both the electronegativity of the oxidized and the reduced species. So with this, I would say, simple qualitative insight, we can go and propose a simple model to try to predict oxidation potentials in terms of electronegativities, where we can combine both electronegativities with the same weight both, or with a different weight on one of them. And we can use to do this, for example, Mulligan electronegativity, meaning an electronegativity that has no information whatsoever on the environment, or we can use our model for the electronegativity when we actually have the information of the environment built into our model. We are actually going to compare our results with the work of Moens and collaborators, and they use 2 different models, one based on the electronegativity equalization principle and what we will take as the benchmark for our calculations, and that's just a model to predict oxidation potentials based on Marcus charge transfer theory that we know has a very strong physical foundation. And also we are going to be considering a really simple model proposed by Mendes Hernandez et al. A bit more recently. So we took all these models and we fit these models using a training set of 31 redox reactions. So we found the parameters for every model using this set, and then we tested those results on a test set of 10 different reactions. And it is worth noting that actually in the test set we have chemical functionality that is not present on the training set, meaning that this is actually going to be a really like a strong test of the validity of these models that we're actually testing on molecules that they have no information whatsoever. And also notice that we are actually considering two different solvents. So we are mixing a lot of variables in this process. So when we analyze the quality of the fitting over the training set, there is actually not a model that is clearly outperforming the others. So they all sort of behave in an equivalent way. But this changes immediately when we consider the results over the test set, when it is pretty clear that the Marcus model, that is the one that we actually were expecting to be the best model, because it's the one with the strongest physical foundation, and the model that we propose with electronegativity is actually taking into account the interaction of the environments, are the two best models over all the range of different statistical measures that we're actually considering. And this comes to no surprise, because actually we can show that our model contains Marcus model as a limiting case, meaning that this is a really strong proof that we actually need to consider the impact of the environment over the electronegativity of the system to being able to actually describe the charge transfer processes that we're taking, that we actually want to analyze. And we prove this both in an analytical way and also doing like a 20 more numerical tests. So up to this point, and to give some short and general conclusions, we have shown that conceptual DFT is actually giving a pretty convenient and general framework to study chemical reactivity and charge transfer. We know that we can obtain new chemical concepts, we can prove chemical principles, even we can find new chemical principles, even more like, even recently, we show that you can actually prove frontier molecular orbital theory starting from conceptual DFT. We also show the key importance of the E versus M problem in conceptual DFT. Like, all these last results started analyzing this really fundamental question of how the energy of a system is changing when we change the number of electrons. In other words, this is obviously is key to studying charge transfer, because charge transfer is essentially how a system is responding to changes in the number of electrons of the spin number. But we also show that this is fundamental to study chemical reactivity. And I really cannot stress this, like overstate the importance of this last sentence. We always keep an eye on physical justification instead of using just this like ad hoc, like mix matching different descriptors with different models, and this sort of like, this is really simple from a computational point of view, but it can really mess up with the physical interpretation and your results. And finally, we prove that we actually need to consider the effects of the environment over the reactivity descriptors. So we cannot go, as people usually do, like and they did for over 30 years, ignoring these perturbations on these descriptors. These are key ingredients in our description of chemical reactivity. So to really conclude, I said at the beginning that I will say why actually we should not be calling this framework conceptual DFT. And the key in all this question is that the main magnitudes that we're working with, say the energy or the electron density, are actually observables. So we can actually measure the energy and we can actually measure the electron density of a system. Meaning that we can essentially use any electronic structure method. So we can use copper cluster, we can use perturbation theory, we can use configuration interaction to obtain an energy or an electron density, and we can do conceptual DFT using our initial results. So this is even more general than the name itself is selling this framework. So we are not bound by DFT. We can actually use all this framework with other electronic structure tools. And well, to conclude, thanks to all the different institutions, thanks to the people giving them the money, and actually to the people of the ARES Lab, mostly for setting up this presentation and helping with everything. So that's it.